Good afternoon, everyone. We will start our discussion for week 7, Power System Engineering. So, firstly, we'll see the brief concepts that will be useful for solving this week's assignment, and followed by that, we'll see some of your doubts, if any. So, for this week, our topic is mainly distribution system load flow, right? Distribution system load flow. So, before that, let us first discuss what is this load flow algorithm. So any load flow algorithm or power flow algorithm for either the transmission system or the distribution system. So the input to this algorithm is basically the line parameters, right? That is the resistance, reactance, and shunt susceptance B naught, basically what we say. So and of course the from bus or sending end and receiving end or two bus of the line. So this line parameters you need. Apart from that, we need the load data. So we need to find out that at which bus loads are connected and what is their value and their active and reactive parts, basically PD and QD. That is from the load end side. And additionally, we also need the generator data that we say. So buses at which generators are present and their generated powers, generated active and reactive powers. So using these uh, as input, the load flow algorithm basically we use to compute the state of the power system. And what are this state for the power system? Basically, we have two states, that is your voltage magnitude and the voltage angle. That is, we generally write it as mod V and angle delta. So this is the output that we get from the system. So these utilizing these states, we can basically, this is again input to other power system studies. So this is the basic one, and from this we can observe whether the system is in maybe correct condition or not, if the voltages are within range or not. Then coming to this transmission system load flow and distribution system load flow. So for the transmission system, we the fundamental parameters of the line, that is the ratio of the line resistance to the reactance, is usually small, or we say it is less than 10. Whereas for the distribution system, this ratio for R by X is greater than 1. So what happens due to this feature of the distribution system is that previously we studied for transmission system load flow algorithms such as Newton-Raphson or your decoupled load flow or fast decoupled load flow. So for this algorithms, the assumptions that we take, we assume that your R by X ratio is small, And taking that assumptions, we derive the equations for this fast decoupled load flow. And for Newton Raphson, you know that we compute the Jacobian and all, and these are all iterative methods. Iterative methods. So what will happen that if we use this Newton Raphson or first decoupled load flow for the distribution system, that because here the R by X is not small, so all these algorithms, Newton Raphson fast decoupled load flow, so this will not be able to be used for distribution system. So they will fail to converge. They will fail to converge because basically the Jacobian matrix that you compute in Newton Raphson or this B dash and B double dash matrix that you compute for fast decoupled load flow. So these matrices will be ill conditioned for this distribution system, and due to this, the Newton Raphson or fast decoupled load flow will not be able to converge for distribution system. So for this, we will study separate algorithms for the distribution system. So basically, we will be studying here what is known as popularly the backward forward sweep algorithm, and another method too, which is similar to this. So basically, for backward forward sweep algorithm, the output will be both the voltage magnitude and the angle delta. But for method 2, we'll see that the output will only be the voltage magnitude. There will be no delta here. So if you want to only monitor the voltage magnitudes, you can use method 2. So let us first see this first method, method 1, which is the backward forward sweep. So for that, let us consider a distribution system. And another thing is that I forgot to tell you here, the transmission system are mostly radial in nature. Means the topology is, sorry, is for transmission system, it is mostly meshed, right? Whereas for the distribution system, the topology is radial or sometimes weakly meshed. So for this load flow, we will be basically exploiting this radial topology of the system, and using this we'll generalize algorithm for computing the voltage angle and magnitude. So for the backward forward sweep method, let us take a system, 4-bus system. So let's say it is this way. So 1, 2, 3, and 4. Let the load connected here be S2, which is basically P2 plus JQ2. This be S4, P4 plus JQ4, and this is your S3, which is P3 plus JQ3. So we have load connected at bus 2, 3, and 4, whose value you know. So for this, the bus 1, we normally take it as the substation or the head of this distribution system. So we assume that we know the voltage magnitude and angle at this bus. So V1 we take as 1 angle 0 in per unit, And considering this V1 as 1 angle 0, we will compute the values for voltage at bus 2, 3 and 4. So basically this you know the line parameters, that is Z12, Z23, Z24. So these are the impedances of the line. So Z12 is the impedance of line between 1 2 bus 1 2, Z23 is the impedance between bus 2 3, and Z24 is the impedance between bus 2 4. So this is understood that this Z is basically R plus JX, where R and X are resistance and reactance of these lines. So this additionally the value of this load connected at bus 2 and 3 and 4. Yes, so this is your data, that is your known values. Now from this we will calculate the load currents. So let's say this load current is I4, this load current is I3, this load current is I2. So basically this I2, you know that V2 into I2 conjugate you get as S2. So if I take conjugate both sides, this is V2 conjugate, I2 conjugate of conjugate will cancel out, and you get as S2 conjugate. So from here I will get I2 as, so S2 conjugate means it will be P2 minus JQ2 divided by V2 conjugate, right? So for this first iteration, basically when you start the first iteration, so we consider a flat start similar to the transmission system load flow also. So flat start means we assume that the initial voltages at bus 2, 3 and 4 is 1 angle 0. So here for I2 in first iteration, you will put the value of first iteration here. V2 in first iteration and its conjugate. So V2 in first iteration is 1. So basically I2 in first iteration will be just P2 minus JQ2. Now similarly you can find the value of, let me write it in small because here I had written in small. So this is I2, I2, I2. Similarly I3 you will get as P3 minus JQ3 divided by V3 conjugate in first iteration. This is first iteration, and for first iteration you will take the value of V3 at 0th iteration. Similarly for I4 in first iteration I will take it as P4 minus JQ4 divided by V4 in the 0th iteration, or the initial, which we take as 1 angle 0, right? So once computed this load currents, then in the next step we'll calculate the branch currents. So Branch currents means the current flowing in the branches. So here, what are the branches of the system? So if I write here, so branches are branch 1 is connected between bus 1 to branch 2 is connected between bus 2 3, and branch 3 is connected between bus 2 4. So I will represent this current as capital I12, capital I23, and capital I24. So if we apply simply the KCL here, so let us move to the next slide and let me then draw it for you. So this was bus 1, 2, 3, and 4. So writing the KCL at bus 3, so I will get the current here flowing from I2 to I3. So that is same as this load current here, I3. So this is I3, this is I4, this is I2. Small are the load currents and capital are the branch currents. So similarly, KCL at bus 4. So I24 is same as I4. And again, KCL at bus 2. So then here I12 is equal to I23 plus I24 plus this load current I2. So this is basically I12, this is I23, and this is I24. Right, so incoming current is equal to sum of outgoing current. So from here, so you can calculate the value of I2. So this is at the end of first iteration. So this was the backward step. So starting from the basically at the end of the feeder or at the tail end of the system, we start computing the load currents and then we write the KCL backwards from the last bus towards the head node. Right. Then we will go forward for calculating the voltages. So this was the backward step. So backward. And now we will go with the forward step for calculating voltages. Backward for I, forward for V. So once I know the branch currents, I can write the voltages. So basically, what will be V2? V2 will be V1 minus the drop in the line 1 2. So what will be drop in line 1 2? It will be I12 times Z12. Right. So that will be in first iteration. So V1 you know already, right? It was 1 angle 0. So I2 in first iteration and Z12 you also you know. Now coming to V3. So what will be V3? V3 will be V2 minus the drop in line 2 3, which is I23 times Z23. Now V4 will be V2 minus I24 Z24, right? So from this, basically you will get the value at the end of first iteration for V2, V3 and V4. So similarly for the next iteration 2, what you will do? You will again calculate the load currents, but here instead of V2 0, you will consider V2 1. So and so again compute the load current considering the voltage at the end of first iteration V2 1, V3 1 and V4 1. And then again you will repeat the step from load current, you will get the branch current, and from there you will get the node voltages. This is the backward one and voltages in forward direction. So at the end of second iteration, so then you will get here V2 2, V3 2 and V4 2. So likewise you will go iteratively, but when to stop? When to stop this contribution, that is the terminating criteria. So for that, what you will do, you will compute the difference absolute, basically absolute of V2. Let's say you are in the ith iteration minus V2 in the previous iteration, and similarly for V3 in the ith iteration and in the previous iteration, similarly V4, and what you will do, you will take the maximum of this absolute values, maximum, and if that is less than equal to epsilon, where epsilon is your error magnitude that is acceptable, or we tell it as convergence limit. So convergence limit, so that may be in the order of 10 to the power minus 4 or something like that. So if whenever this is satisfied, this condition, when the maximum of absolute of the voltage between the previous iteration and the next iteration is less than epsilon, so we stop. So I hope this was clear. Now for method 2. So here all these are complex quantities, right? So you will be getting voltage magnitude and the angle. But sometimes what happens, or mostly in the distribution system, the variation of this voltage angle delta, voltage angle delta is not significant from the starting or the head of the feeder to the tail end. It's not very significant. So they will be always close to zero only. So what mostly we are interested is in knowing the voltage magnitude. So if we want to calculate the voltage magnitudes only at the nodes, if you want to calculate the voltage magnitude only, Then we go for method 2. So what is this method 2? Let us discuss. So let's say we'll see one generalized case, so one small one. So let's say the voltage is V1 here, and this is V2 here, angle delta 1, angle delta 2. So from here I can calculate the current flowing here, I1, as difference of voltage between the buses, V1 minus V2, by its impedance Z1, right? And also, let's say you had a load here, P2 plus JQ2. So we had seen that V2. So I will represent this one as V1 bar, means it is complex quantity. Similarly, V2 bar is complex quantity. So V2 into I2 conjugate is P2 plus JQ2, or we had seen this previously, I2 you will get as P2 minus JQ2, taking the conjugate basically and dividing here. So this is V2 conjugate, right? This is 1. So we will compute, basically equate these two equations, equation 1 and equation 2. So if I do that, what I'm getting, basically first equation was V1 minus V2 divided by Z2. So let Z2 be, or it is Z1 only, Z1, yes. So it is R1 plus JX1. And from the second equation, we got I1 as P2 minus JQ2 divided by V2 conjugate, right? So let's say we then cross multiply this two. So what I will be getting, V2 conjugate V1 minus V2 equal to R1 plus JX1 P2 minus JQ2. So again, if I, yeah, so we know that for this V1, so V1 is basically V1 magnitude angle delta 1, and this I can write as V1 cos delta 1 plus J V1 sin delta 1, right, in the rectangular form. So when I write this and multiply here, so what I will be getting is So multiplying this, so their magnitude will be multiplied and their angles will be added. So here I will get V1 V2 cos of basically delta 1, and this is a conjugate, means it will become minus delta 2. Similarly, V1 V2 j times sine of delta 1 minus delta 2 plus V2 square, and here minus delta 2 and plus delta 2, so they will cancel out here, right? This will be minus V2 square. Yeah, so that is, here it was P2 minus JQ2, so that will be R1 P2 plus JX1 P2 minus J R1 Q2, so minus J square will be plus, so X1 Q2. So from here, if I basically compare this real and imaginary parts in both the equation and both the sides, comparing real and imaginary parts on both sides of equation, on both sides. So here the real part is V1 V2 cos delta 1 minus delta 2 minus V2 square. So V1 V2 cos delta 1 minus delta 2 minus V2 square, and here real is R1 P2 plus X1 Q2, R1 P2 plus X1 Q2. What about the imaginary part? It is V1 V2 sine delta 1 minus delta 2. So V1 V2 sine delta 1 minus delta 2. So that is here X1 P2 minus R1 Q2. X1 P2 minus R1 Q2. So this one I can rewrite as V1 V2 cos delta 1 minus delta 2 is V2 square plus R1 P2 plus X1 Q2. So this is my equation 1 and this is equation 2. So squaring and adding these two equations, so squaring and adding, basically in the first part you will get V1 square V2 square and the sine square plus cos square term that will go out, that will be equal to right side. So let me consider this as one and this as the second term. So what I will get as V2 power 4 plus R1 P2 plus X1 Q2 whole square plus 2 V2 square R1 P2 plus X1 Q2, right? And from the second equation I'll get X1 square P2 square plus R1 square Q2 square minus 2 R1 X1 P2 Q2. So let us simplify this. So V1 square V2 square V2 to the power 4 plus I'll expand this further, then it will be R1 square P2 square plus X1 square Q2 square plus 2 R1 X1 P2 Q2 plus 2 V2 square R1 P2 plus X1 Q2 plus X1 P2 square plus R1 square Q2 square. So you can see, sorry, minus 2 R1 X1 P2 Q2. So from here, these two terms, they will cancel out, right? And let me then collect the coefficients of V2 basically. So here V2 to the power 4 plus, let me collect 2 V2 square. So this will be R1 P2 plus X1 Q2, and this part, it will come to this side, so it will be minus times. So 2 is common here, so I'll divide by half and V1 square. Right, so these two terms are gone. Now for the constant part, so here you can see also R1 plus X1 square, they will come as common. So R1 square plus X1 square into P2 square plus Q2 square. So this you get the final equation equal to 0. Now for this, you have V2 to the power 4, means this will give 4 solutions of V2, and from that the acceptable solution basically, which will be positive among those, so that will be solution of V2 that you get is basically P2 R1 P2 plus X1 Q2 minus 0.5 V1 square whole square, then minus R1 square plus X1 square P2 square plus Q2 square to the power of half, again minus R1 P2 plus X1 Q2 minus 0.5 V1 square to the power of half. So here remember, this V1 is basically the magnitudes. These are all magnitudes, right? Here I had written V1 was the magnitude and delta 1 was the angle. So from here, we have eliminated the angle parts, the delta 2 and delta 1, and we get only the equation in terms of magnitude. So using this relation, we will see the second method basically. So from here we defined two terms basically, that is T and A. So the V, so V at the receiving node basically. So this is the fine, this is the receiving end, this is the sending end. Let me write it as M2, this is M1, M2, and this branch is JJ, let's say. So V receiving end basically VM2 magnitude you will get as DJJ, which is the branch number, minus AJJ to the power of half, where this AJJ is basically the resistance of that line, the receiving end here, the PM2 and JQM2. So PM2 plus XJJ QM2 minus 0.5 at the sending end, right? So VM1 square and Tjj will get us Ajj square minus R square plus X square into P square plus Q square whole to the power of half. Right. And furthermore, we had seen that I1 was P2 minus JQ2 divided by V2 conjugate. So if I take the magnitude, here it will come as P2 square plus Q2 square divided by V2 square. And for the losses, active power loss, we write as R I square, and reactive power loss is basically X I square. So if I square and then add R here, multiply R here, so it will be R of the first line, right? R1. So here this is branch 1, right? Or branch 1, R1 I1 square is equal to R1 P2 square plus Q2 square divided by V2 square. So that is your P loss in the branch 1. And similarly, the Q loss will be x1 I1 square is x1 into P2 square plus Q2 square divided by V2 square, which is basically Q loss in the first branch. So from here also you can write the generalized equations. So P loss in branch JJ, receiving end M2 and sending end M1. So P loss in the branch JJ is RJJ into P M2 square plus Q M2 square divided by V M2 square. So what we do here basically, let's take the same system. Excuse me. Yes. So if you compute the total real power load injected or fed through node 2, Basically, how much power you are injecting at this node 2. How much power you have to inject? Let me write it as P total 2. So from here you need to supply all these loads at the downside, right? Downstream to this branch. So basically, what are the loads then? So P2, that is at the same node, and then downstream nodes, that is P3 plus P4. Then additionally, along with this load, you also need to supply the losses through the line, which are downstream. So from bus 2, the branches that are downstream are branch 2 3 and branch 2 4. So P loss 2 3 plus P loss in 2 4. So that is the power injected or fed through node 2. Similarly, so same equation you can write for Q also, right? For the same node 2. And if I write for node 3, so for node 3 only you need P3, right? And for node 4 I need P4. So same will be for Qs also. Now let's say this concept we'll use. So for computing the first iteration, iteration 1, we assume that the losses are 0 in this line. So we assume P loss in 1 2 equal to P loss in 2 3 equal to P loss in 2 4 is 0. So taking this losses as 0, we compute the P total at the P total and Q total at the receiving nodes of all branches, right, using this formula. Now once you calculate this P total, then I can calculate this A and D here. You see this one. So once this P total and Q total are calculated, so I can then compute the A and D. So for first iteration, first branch, it will be Vm1 is sending end voltage, so that will be 1, right? So in the third step, compute the AJJ for all the branches and DJJ for all branches. And once you know that, you can calculate the V at the receiving nodes, that is M2, from or using this A and D, right? This formula basically here, this one, right? V receiving. Now, once you have calculated this, then again you can calculate the losses at the end of first iteration using this formula. Because here you know V2 now, Vm2, from that you can calculate losses. So calculate P loss and Q loss in this branch JJ basically using Vm2. So that will be the end of your first iteration. And For iteration 2, again you take now the loss as P loss Jj in iteration 2 computed at iteration 1. So this was iteration 1, and Q loss at the second iteration as computed in the previous iteration. And once you know the losses, again you can calculate the total real and reactive power injected at each node, and from that again this process will continue iteratively, and here the convergence criteria will be, or termination criteria is when the maximum of absolute of P loss in ith iteration minus P loss at previous iteration and absolute of Q loss iteration for all the buses of all the branches, maximum over all branches is less than equal to your termination convergence limit. So then the iterative process will stop. So this is your method 2. Now we will see the questions here from the previous assignment. So this will be only using these two methods, method 1 and method 2. So in method 1 you get both the voltage angle and magnitude. In method 2 you only get the voltage magnitudes. So for distribution network, normally X by R ratio is, so I told you that R by X ratio is large for distribution system. So R by X is normally greater than 1, so X by R will be less than 1. Whereas the same for transmission system, this X by R is very high. Sometimes for it may be in the range of 20 or 50 also. So but for distribution system it is very low, X by R ratio is less than 1. So this C. Now next question. So the distribution network is represented by list of sending and receiving end nodes as given in table. Node 1 is connected to main grid. So what are terminating nodes present in the network? So these kind of questions you can draw this network using this data. So first is, so this is the substation node 1. So from node 1, what are the line connected? 1 is connected to 2, right? So I'll connect to 2. Then from 2 I have 2 to 3. Then 3 to 4. 3 to 4. Then again 2 to 9. So another here branch, lateral branch that we tell. So 2 to 9. Then 4 to 5. Again this is 4 to 5. 5 to 6. 5 to 6. 6 to 7. 6 to 7. 4 to 11. So another lateral is 11. Then 7 to 8. Again 7 to 8. Then 11 to 12. So this one. Then 6 to 13. Another lateral branch. 6 to 13. Then 13 to 14. 13 to 14. Then 9 to 10. 8 to 9 was not there. Oh, 9 is here. Yeah, 9 to 10. Then 14 to 15. 14 is here. So here terminating node means no lines are present ahead of it, right? So from here you can see which are such. So bus 8, because इसके आगे ahead of this you don't have any more lines connected. This is the end here. Yeah, and the next one is this 10, 12 and 15. So here this is option C. Now, yeah, so question 3 says a distribution network is represented by list of sending and receiving and nodes. Node 1 is connected to main grid. Find number of nodes present in network beyond branch 6. So is this the same one? 1, 2, 2, 3, 3, 4. No, this is the different network. So let us draw this network. So first is from 1 to 2, 1 to 2, 2 to 3, 2 to 3, 3 to 4, then 8 to 9. But 8 is not in the receiving end side, right? I don't know how this 8 to 9 is coming. I think some datas are missing here, or we will find in the end after we draw this. Basically, we'll get it 4 to 5. Let me draw. Then 5 to 6. Then 3 to 7. I have node 3 here. So 3 to 7. 5 to 10. 5 to 10. 7 to 8. Right now I don't have 7. Yes, I have 7. 11 to 12. I don't have 11 right now. Let me go back up here. 8 to 9. Yes, I have 8, 9 now. So 10 to 11. Yes, I have it. Then 11 to 12. So this is my structure here. So it is saying that network number of nodes present becomes branch 6. So which is branch? Yes. So okay, let me draw once again. 11 to 12 I don't have. 8 to 9. 8 to 9. 10 to 11. Then 11 to 12. Okay. And it was saying branch 6. So which is the branch 6 here? Between 4 and 5. So this is your branch 6. Right. So number of nodes present beyond branch 6. So how many nodes are present beyond branch 6? So this will be all these, right? All these set of nodes. So they are bus 5, 6, 10, 11 and 12. All these nodes so how many these are 5. So 5 nodes are present beyond 6. beyond branch 6. Now next one. So here, given 2-bus network, line data and load data are given in per unit. Voltage magnitude is 1 per unit. Determine active and reactive power loss. So basically this will be method 2, because only voltage magnitude is given and losses are asked, which was in method 2. So from method 2 we got this, right? A and D we first need to calculate. So let me call this as branch 1, 2. Now this is branch 1 simply. So A1 was PM2. M2 is receiving end, right? This is M1, this is M2, this is JJ. So what is P2? Then R1 plus Q2 X1 minus 0.5 V1 square. So that will be P2 is 0.9. This is P2. This is Q2. R1 is 0.087. Q2 is 0.6. And X1 is 0.054. Then minus 0.5. V1 is 1. So 1 square is 1. So doing this, we will get it as 0.9 into 0.087 plus 0.6 into 0.0054 minus 0.5. This is coming in negative, minus 0.41846, and D1 will be A1 square minus R1 square plus X1 square into P2 square plus Q2 square and whole square root. So here if we put the same values, I'll get square root of A1 as 0. minus 846 square, yeah, minus R1 square plus 1 square into P2 is 0.9 square plus 0.6 square whole square root. So this gives me 0.4035343. Now from this I can calculate V2, right? So what is V2? V2 is D1 minus A1 whole square root. So that will give me as D1 minus, that will be plus 41846, that is second, D1 is 0.40353 plus 0.41846. So that is mostly 0.9068. It is not matching with the answer. Let me recalculate the values first. So it is P2R1, P2.9, P2R1 plus Q2 X1 minus 0.5. So sorry, this is 0.3893. So using that, again, let me calculate. So 0.3893 square minus R1 square, 0.9 square plus 0.6 square into 0.08, 0.087 square plus 0.054 square. So this gives me 0.3732. So 0.3732 plus 3893. Yeah. So I get it as 0.8732. Now once I know the V2 from here, I can calculate loss, right? P loss 1 in branch 1 is R1 P2 square plus Q2 square divided by V2 square. So that I will get as 0.087 into P2 square plus Q2 square divided by V2 is 0.8732 square. So I get it as 0.1335 per unit. All these are in per unit. And Q loss is X into this quantity, V2 square plus Q2 square divided by V2 square. So X, I just need to change X, is 0.54. So that comes to be 0.0829 per unit. Is this correct? Yes. So loss 0.13. So I think first one is correct. Excuse me. Okay, let's move on now. So fifth question. So a DC Ringman distributor is supplied through a feeder SA and is loaded as shown in figure below. So, and load are tapped off at points B, C, D, points B, C, D. Interconnector is placed between A and C, and S is the feeding point maintained at 280 volt at S. The resistance are given. Determine voltage at load point C. Okay, so here let us assume this current is I1 or I. So basically we need to apply KCL here, right? Let this be I1 and this be I2. So at B, if I write the KCL, it is I1 plus IBC, and let me know BC is in the other direction. Let me assume then I1 is 12 plus IBC. So IBC will be I1 minus 12. Now at C, or at D, let me write down. So I2 equal to 18 plus IDC. So ID to C will be I2 minus 18. Now at C, so IAC plus I1 minus 12 plus I2 minus 18 equals to 20. So IAC will be 20 plus 18 minus 12 minus 7 minus I2. 20 minus 12, 8, 12. Oh, sorry, reverse. So this is also no here. Sorry, let me. I have this I basically here, so let me write it in those terms instead of writing in I1 or I2 terms, because then I'll get the relation I is I1 plus I2. So let me write that. I'll write the KCL at A. So I is I1 plus I2 plus IAC. So IAC I'll get as I minus I1 minus I2. Now let us write the KVL. So VS equal to VA plus I, and the resistance is 0.6, and what will be I will be basically 12 plus 20 plus 18. So that gives us 40, right? No, 50. So you know VS is 280, so VA is 280 minus I is 50.6. So that will come out as 250. Now KVL in loop ABCA. So starting from A, it is 0.4 I1, 0.8 I1 minus 12 minus 0.8 I minus I1 minus I2, or I can write as 50, right? So from here I will get 0.4 I1, 0.8, 1.2. How much is 0.8 into 50 is 0.4. So 0.4 will cancel out. So I'll get 0.48 equal to 0, right? 0.8 I1, 12 96, 9.6 minus 4 minus 0.8 I1 minus 0.8 I2 is 0. So I'll get 0.4 I1 minus 0.8 I2 equals to this is 40 here. This is plus, this is plus. So 1.6 plus 4, sorry. So 1.6 2 I1 plus 0.8 I2 equal to 49.6. This is equation 1. And for equation 2, let me write the KVL in ADCA in the lower loop. So I2 0.4 I2 plus 0.4 I2 minus 18, then minus 0.8 I minus I1 minus I2, that is equal to 0. So again here I will get as 0.4 I2, 0.4 I2, 0.8, 1.6 I2, and I1 is minus 0.8 plus 0.8 I1, and I is 50 basically. So that will be equal to 40 plus 7.2, 47.2. So this is equation 2. Then solving this I1 and I2. So basically you get I1 as 16.25 and I2 as 21.375. So voltage at C, VC is VA minus 0.8, 50 minus I1 minus I2. That will be 240.1. So answer B. Now next question. Is this the same? 6484, 648484. Yeah. So determine power loss in the system. Combination of feeder and ring main. Means power loss in this branch, this and this. So what will be power loss? Will be I square R. The total power loss will be 0.6 I square plus 0.4 I1 square plus 0.4 I2 square plus 0.8, 50 minus I1 minus I2 square plus 0.8 I1 minus 12 square. We just left this one plus 0.4 I2 minus 18 square. So how many? 5, 6, 2, 3, 4, 5, 6. Okay. So from previously we have calculated I1 and I2 in previous question. So just substitute those values here and you will get the total power loss as how much you get here. 16 and 21. Yeah. So here I get as 1929.90 watt. So which is option D. Now next question. So here sample 3 bus network is given below with line and load data given. Use method 1 to solve the problem, that is backward forward sweep. So in backward forward sweep, what was the first step? So firstly we need to convert everything to per unit here, right? So here you know Z base is kV square by MVA. So what is your voltage level here? 11 and MVA is 1. This will be 121 ohms. So for Z12 in per unit is equal to Z12 actual by Z base. So let's say you will get that as 0.0221 plus J 0.0084 per unit. Similarly, Z23 you will get 0.0288 plus J 0.0095 per unit. So, and you need to also calculate the load demands in per unit, right? So P2 or S2. Base MVA is 1, so it will be as it is only. So here this is in kilowatt basically. Sorry, not watt, VA, because this is apparent power, right? So you get S2 in per unit as this divided by your base, which is 100, right? 1 MVA is 1000 kVA. Dividing this by also 1000, so I get it as 0.2 plus J 0.1 S3 as 0.1 plus J 0.08 per unit. So once you have everything in per unit, so I will assume this V1 as 1 angle 0, right? For method 1 we have both voltage magnitude and angle. So after that we will start our calculation of load current, which is the first step. Load current. So let's say this is my I2, this is I3 load currents. So I2 will be S2 or P2 minus JQ2 divided by V2 conjugate, right? And for first iteration we'll assume V2 V3 as 1 only. So this will be same as P2 minus JQ2. I3 will be also same as P3 minus JQ3 divided by V3 conjugate. That will be P3 minus JQ3, because for first iteration V2 first iteration, 0th iteration, V3 0th iteration is 1. So this is first, this is 0, this is 0. So once you calculate the load current, the next step is branch current, right? Branch current is the backward step. So for branch current, what I will get I23 as same as I3, and what is I12? I12 is same as I23 plus I2, which is same as I2 plus I3, because I23 is normally I3 here, right? So once you know the branch currents here, at the first iteration, so now you'll calculate the backward step, forward step, which is voltage. Node voltage. So for that, what I'll write, V2 is V1 minus Z12 I12. So this all you have calculated in above, and V3 will be V2 minus Z23 I23. first iteration. This is always 1, right? 1 angle 0. First iteration, first iteration, first iteration. So once this is iteration 1. For iteration 2, what you will do? Again, you will calculate the load currents, but here instead of V2 at 0, you will put V2 at 1, right? So I'm not calculating the values here. You can follow the same process. So it is asking for 1 iteration or 2 iteration. Find the voltage at bus number 3 after second iteration. Now, same question actually. So after second iteration, compute active power loss. Consider line number. Okay. So we have calculated after solving the previous one. So you will get second iteration values. Now using these values, you will compute the losses total. So P loss total will be P loss in line 1 2 and P loss in branch 2 3. So or additionally what you can write Q loss is Q loss 1 2 plus Q loss 2 3. So here this will be basically I12 square x12 I23 square x23. This is I12 square R12 I12 square R23. Or you can write the power balance equation also. That is your P input equal to P total plus P loss. So for this input power, that is at this substation or bus 1, what I can write P input here, how much it will be? It will be real part of V1 I12 conjugate, right? So this will come out as, and these are at the second iteration, right? Second iteration values will put basically. Then you will get a P input as 0.30319 per unit. Now once you know that, what is your P output? That is your 200 plus 100 kilowatt, 300 kilowatt, or zero point 0.3 per unit. So what will be P loss? That will be input minus output, that is 0.30319 minus 0.3, that will give me 0.00319 per unit, or multiplying by 1000, it will give me as 3.19 kilowatt. So which is option B. Now next question. So same है क्या? Yes. So line all given. Yeah. So sample distribution system. Use method 2 to solve the problem. Consider substitution voltage as 1. So for method 2, you will be calculating only the voltage magnitudes, right? And we'll consider the losses here. So initially, yeah. Hmm. So initially here we assume losses as 0, right? So initially P loss, Q loss in both the branches 1, 2 and 2, 3, these are 0. So from here what we will do, first we will calculate this P2 and Q2, right? So if loss is 0, so we had seen no that P3 total, so that will be load that is here 100, or if I convert into point per unit it will be 0.1 plus no losses here ahead of this line, right? So only 0.1. And what about P2? P2 will be so will be this load 0.2 plus loss in line 2, 3. So this is we have considered here 0, right? In first iteration that will be 0.2. Similarly Q3 will be 0.08 and Q2 will be 0.1. So once we have calculated this, then we'll calculate the A and D, right? So A for branch 1, this is branch 1, branch 2, so that was P2R1 plus Q2X1 minus 0.5 V1 square, and similarly D1 you can calculate here as A1 square minus R1 square plus X1 square into P2 square plus Q2 square whole square root. And what about A2 and D2? So I think we miscalculated P2 and Q2. So that was the total active power injected at node 2, right? So P2 will be this load, if I call it as PD2, PD3. So it will be PD2 plus PD3 plus the losses in line 2, that is line 2, 3. P loss in line 2, this branch 2. So this we have 0, so it will be PD2 plus PD3 that is 0.3. Similarly for Q2 we will get 0.18. So Similarly, A2 you can calculate as P3R2 plus Q3X2 minus 0.5 V2 square. D2 is, you can write here half. So after calculating A1 and D1, you can calculate V2 using the relation. It was, I think, D1 minus A1 square root, and that V2 you can substitute here, so that you will get V3 as D2 minus A2 to the power half. So this after first iteration it is asking, or two iterations, second iteration. So similarly you will do the second iteration also, and from that, after calculating that, basically you will get the loss. So after first iteration, what will be the loss? P loss 1. So that will be P loss 1 for branch 1. So that will be R1 P2 square plus Q2 square divided by V2 square. And what about P loss 1 for branch 2? That will be R2 P3 square plus Q3 square divided by V3 square. That these are at the end of first iteration. So these values you will substitute, so that you can calculate. This is after first iteration. Whole process again you will repeat, so that you can get after second iteration. Now the last question, it is the same, and here it is asking total reactive power loss after second iteration. So Q total equal to total loss equal to Q loss 1 to, this is branch number I am writing, Q loss 2 3, and here all values you will use after second iteration. So that will be equal to R1 P2 square plus Q2 square divided by V2 square, sorry, this will be X1 plus X2 P3 square plus Q3 square divided by V3 square, right? So substituting all these values, that is second iteration values for V, so you will get final answer as 1.26 kVAR. So that will be option A. Okay, so these were the assignments for assignment question for this week. So I hope all both the methods, method 1 and method 2, were clear to you. We will discuss next in the next week about next week 8. So I think we'll close the session. I think we will close the session now.